Hello, my name is Asma binti Abd Rahman and I am a student in University Putra Malaysia taking Bachelor of Electrical and Electronic Engineering with honours. So today I would like to share with you about my final year project with title Magnetic Sensor for Wireless DC Current Probe. So my problem statement is cables from current clamps to a multi-channel data logger unit in a transmission station is cluttered. And second, the safety of data logger operator is at risk if the equipment is not handled properly. So my objective is first to design and test a wireless DC current probe, focusing on probe sensitivity and wireless transmission range. And second, to propose a PCB layout of the wireless DC current probe system. So this is my proposed design, where my first block is clamp or focusing on Hall sensor and unity gain buffer. Second is microcontroller, which I use Arduino Uno. Third is transmitter circuit, and then receiver circuit, and then a customized display program. So Hall sensor, this is the setup that I used to experiment. I use 49E Hall sensor, and to provide a constant magnetic field, I use a magnet to simulate the magnetic field in a conductor. So I use formula Ohm's law of resistance, where I use it to calculate current, and then from there I calculate magnetic field, and then I relate it to the magnetic field obtained from the sensor using DC offset minus output voltage divided by sensitivity of the sensor. So to simulate the Ohm's law of resistance, I supply 5 volt 800 ohm resistor, and then I obtain 48.1 milliamp. And when I supply 5 volt at 200 resistor, I obtain 34 milliamp. From here, we can see when the resistance increase, the amount of current decrease. And when I supply 8 volt at 1 kilo ohm, I obtain around 8 milliamp. And when I supply 10 volt at 1 kilo ohm, I obtain around 10.1 milliamp. So from here, we can see when I increase voltage, then the current also increase. And so in overall, when the current is proportional to voltage, directly proportional, and while it is inversely proportional to resistance, and the magnetic field is directly proportional to the current. So this is the graph that I obtained when I increase number of magnet to monitor if there is changes. When number of magnet increase, then the voltage measured also increase. And when I test using different polarity of the magnet, for south polarity I obtain between 2.65 to 4.3, and for north polarity I obtain between 2.65 to 0.9 volt. So the linear region of the sensor is between 0.5 cm to 1.5 cm, which corresponds to an output of 4.28 volt and 3.16 volt respectively. And the sensitivity of the sensor is 1.12 volt per centimeter. And when I check the quiescent output voltage, which is the voltage without magnet, it is also called as DC offset. It is almost equals to the half of the voltage supply that I supply on the circuit. This is the plot that I get when I calculate the magnetic field. So the negative indicates the polarity of the magnet, which is south pole. From here, we can see that when the magnetic field increases, the voltage also increases. The sensitivity of the sensor is 1.8 millivolt per Gauss. Unity gain buffer, this is a schematic where the output voltage is equal to input voltage as the gain is 1. When do we use? To enhance the signal drive strength, and second, to provide a stable input load for the transmission circuit. So this is the circuit I test unity gain buffer, where I connect the positive supply to 5 volt and negative supply to ground, and that is my input voltage, and I measure output voltage there. So this is the plot that I obtained. When I calculate the gain, which is the slope of the plot, it is around 0.9975, which is approximately equals to 1. And then the next subblock is ADC. This is the setup, and this is the flowchart to convert analog to digital value. Why it is important? Because digital value is used to transmit the data wirelessly. When I test the ADC, this is the plot graph, and the range of and the error of the NL is equals to negative 0.1 LSP, and INL is equals to 0.046 LSP. For transmitter and receiver module, I use a HC05 Bluetooth module, which it operates at 3.3 volt, while Arduino Uno operates at 5 volt. So I use a voltage divider to connect the transmitter of the Arduino Uno to the receiver of the Bluetooth module with a ratio of resistance between 1 to 2. So when I test the transmission range from the datasheet, it is between 10 meter to 100 meter. And when I test, when I test across the building, it is around 32 meter. And when I test between building, it is around 56 meter. So when I integrate the subblock together, this is 49 Hall sensor, unity gain buffer, Arduino Uno, and Bluetooth module. So when I compare the output measured at the Arduino Uno and Hall sensor, the percentage error is around 1%. And I plot voltage against current. The sensitivity of the sensor is around 83.33 ampere per volt. So for visualization, I use MIT app. So this is how the display will look like if it is not connected to any Bluetooth module. And when it is connected, it will display the value. So in conclusion, input linear range between 0 ampere until 143 ampere, and output linear range between 2.65 volt until 4.5 volt, and transmission distance around 56 meter. For future work, PCB layout is printed into PCB board and test the board. And the PCB layout of the circuit have been implemented in breadboard is here, where the component needed is Hall sensor, amplifier, Bluetooth module, Arduino Uno, resistance, and also battery. So thank you for listening and watching.